So let's continue chapter 4. We're still talking about proofs, different methods of proofs. Well, so far we talked about using direct method of proof for a universal statement, a counterexample to disprove a universal statement, to find one specific example to prove an existential statement, and also showing that an existential statement is false by taking any random, arbitrarily taken variable from the domain. We talked about contradiction, contraposition. Well, there are some definitions that we need to present. So we can talk about proofs, lemmas, theorems related to those definitions. We still will quotient remainder theorem. So quotient remainder theorem says, well, if we have a number, an integer like n, let n be an integer. And if we take another integer like d, let d be another integer, the quotient remainder theorem assures us that n can be written as the q plus r. Q and r are both integers, and r is bounded between 0 and d. There are unique integers like q and r is bounded between 0 and d. Remember that we said, well, we have a name for these. In this case, we say that d is the quotient and r is the remainder. Well, of course, this course is related to computer science. And as we saw in last week's discussion, we use different programming languages like Java, C, some of you use MATLAB, some others Python, and we presented different connectors using logic in computer programming. So we use mod operator and div operator that they connect discrete math to programming languages. We use mod and div operators. They are connected and related to quotient remainder theorem. Very well. When you write in div d, this is referring to your q, the quotient. When you do the division and you use operator, division, div, the divisor, it's going to give you the q. But when you do n mod d, it's going to be equivalent to the remainder r. Remainder r. We use usually percentage to present this operator in Python. Perfect. So why this theorem is important to us? Why we say that, hey, this is quotient remainder theorem. It happens that quotient remainder theorem can help us to classify the number system. That's the important part of this theorem. So note that. The quotient remainder theorem help us to classify numbers. Well, what's the meaning of that? Let me give you an example. Remember that when we talk about numbers, when I say numbers, I'm talking about integers. If I want to change the domain, I specify that. We call that any integer like n can be classified into two cases, either even number or odd number. So this is either even or this is odd. So we say that a number is even if and only if we can find another integer like k, that n is equal to 2 times k. K belongs to z. And we say that it is odd if n can be written as 2k plus 1. Again, k is an integer. Well, okay, think about it this way. Now that you have your n and it's equal to 2k plus 0, the remainder is 0. All right. Take a look at your quotient remainder theorem. Quotient remainder theorem says, well, I have n equals to dq plus r. It means that if I divide this number by 2, the remainder is equal to 0. If I divide this number by 2, the remainder is equal to 1. So what's the meaning of that? It means that, okay, if this is my number system, here, I can divide it up into 2 cases. One case, one section is all even numbers. 2 cases. The other part is 2k plus 1. 2k plus 1. Or I can say that, hey, this part is the part that when I do the division, the remainder is equal to 0. So all of the numbers, all numbers that are divided by 2 with remainder 0. R is 0. Remainder is equal to 1. So I partition, the official way or the official terminology that you're using is I partition the number system into 2 partitions using quotient remainder theorem. We partition the number system into 2 partitions. 2 partitions. The first partition is the part that when you divide by 2, the remainder is equal to 0. The second partition is all those numbers that when you divide by 2, it includes remainder equal to 1. We can, of course, list some of the numbers there, but it's not going to be very useful. We can use just some representations here, but we prefer to write them in official way. So these numbers, like 2, we can write 4, we can write 10. The rest of the numbers, even numbers. And here we have 3, some numbers, 5, 15, the rest of the numbers. What Okay, so it's better to use the official way of writing even numbers, odd numbers. Okay, now I expect you to ask, what if I continue this process? So this is how mathematician thinks. They think, okay, if I divide by 2, I get 2 partitions. What if I divide by 3? What if I divide by 4? Maybe 5? How about 6? How many partitions do we get? Let us try. Our next step, in our next attempt, we divide by 3. How many partitions do we get? So, we're getting back to quotient remainder theorem. Quotient remainder theorem says, hey, if you're dividing by d, which is 3, the remainder is either 0 or 1 or 2. So we get 3 partitions. Okay. It's a separate case. It's a different thing. When we attempt to divide by 3, we have 3 partitions. We get 3 partitions. The very first partition, 3k. So 3k. It means that the remainder is equal to 0. The second partition, 3k plus 1. 3k plus 1. The remainder, as you can see, is equal to 1. And the last partition is 3k plus 2. The remainder is equal to 2. Like before, you can list some of these numbers, make sure, hey, I get the big picture, what's going on. And note that they have no intersection. And the union of these 3 partitions is equal to the number system that you're working with. So what if I have division by 4? How many partitions I get? Next, we divide by 4, and by using the quotient remainder theorem, these are the remainder can be 0 or 1 or 2 or 3. So we get 4 partitions. Okay, let's take a look at this. 4k, so my number can be 4k, can be written in 4 times k. It means that the remainder is equal to 0, or 4k plus 1. 4k plus 1 r is equal to 1, the remainder is 1, or 4k plus 2. R is equal to 2. And finally, 4k plus 3, remainder is equal to 3. So what if I divide by 5? How many partitions I get? Dividing by 5, the remainder can be 0, or 1, or 2, or 3, or 4. So you get 5 partitions. Now, what if you divide by 6? How many partitions you get? 7. We're all using quotient remainder theorem to do these partitions. So what's the use of these partitioning? Okay. We presented a theorem, quotient remainder theorem, And we saw that we can use this theorem to partition the number system. Well, the use of it is here. We can actually use those to help us prove theorems, a lemma, propositions. In this case, we have a theorem. The theorem says the square of any odd integer, the square of any odd integer has the form 8m plus 1. Has the form 8m plus 1, and m is just an integer. And this is page 3. Okay. So remember what you learned so far. By using Quotient remainder theorem, Quotient remainder theorem, we have different partitions, different classifications for number system. N is 2k, n is 2k plus 1. N is 3k, n is 3k plus 1, n is 3k plus 2. N can be classified to 4k, n can be classified to 4k plus 1, n can be classified to 4k plus 2, n can be classified to 4k plus 3, and so much more. N can be classified to 5k, n can be classified to 5k, n can be classified to 5k plus 1, n can be classified to 5k plus 2, n can be classified to 5k plus 3, and n can be classified to 5k plus 4. Okay, think about it this way. What are we trying to do? We're trying to take any odd integer. What is this? This is a universal statement, right? Universal statement. This is a universal statement. For any, the predicate, it says, hey, if you take any random odd number and you square it, this square has this form. So if you take any random, arbitrarily taken, not one example, a random number, a random integer, like n, then n squared is 8m plus 1 for some integers like m. Which method of proof you prefer for this? And if you want to use direct proof, which odd number you're going to select here? This is my question. So remember that since it's a universal statement, we cannot use a specific example. Specific example is a no-no. A specific example is a no-no. Make sure you never use a specific example for your universal statement. You use counter example if the question says, hey, disprove it. And you try to prove something related to universal statement, you never use a specific example. Perfect. Okay, now remember that you are trying to prove a universal statement and you want to use an arbitrarily odd number which is taken from these forms that you have. Know that if you use 3k plus 1, if I plug in 1 for k, it's going to be 4. It's not even odd. You end up with an even number as well. So, well, let's see. What if I take just n equals to 2k plus 1? But if I just focus on this form, does it cover the rest of the forms? Not actually. So 4k plus 1 and 4k plus 3 covers all of those odd numbers that have 8 times m plus 1. Let's take a look at this. Here, so you start thinking about it. You start writing the steps. If I select 2k plus 1, if I say, hey, n is equal to 2k plus 1, and if I square it, does it even give me 8m plus 1? Does it create that number for me? Let us square it. N squared. N squared is 2k plus 1 times 2k plus 1. So n squared is going to be 4k squared plus 4k plus 1. It doesn't even have 8 here. So this is not the most comprehensive odd number for me. So I have to move on to the next odd number that when I square it, it actually creates 8m for me. So let us use 4k plus 1 and also 4k plus 3. So these two are odd, and if I square them, it's going to create 8m for me. So in this case, I get n squared, which is 4k plus 1 times 4k plus 1. So to write it a little bit more clearly, so n squared is equal to 16k squared plus 8k plus 1. So here between these two, if I factor out 8, I can create 8, which is what I'm looking for. 8, 2k squared plus 4k plus 1. Let's call this guy m, and then we're done. So n squared is equal to 8m plus 1. What if I take this odd number? N is equal to 4k plus 3 and square it. N squared is 4k plus 3 times 4k plus 3. So n squared is equal to 16k squared plus, here I have 12k, 24k plus 9. 9 can be written as 8 plus 1. So 8 plus 1. And n squared is, if I factor out 8, I get 2k squared, 3k plus 1, and outside parentheses, I have plus 1. Let's call this guy m. It's an integer, so n squared is equal to 8m plus 1, and have this next to this one. So I selected the correct format for my odd number, and I eventually am able to prove this theorem. 8m plus 1. Perfect. So let us continue. 4.5. More fun with proofs, actually indirect proofs. Sometimes they have statements that are very hard to deal with using direct proofs. So what do we do instead? We use indirect proofs. Remember that One of them is called using contradiction. Indirect proof, contradiction. One of them is contradiction. How it works, we say that, hey, suppose the conclusion is wrong. So the technique is that assuming the conclusion is wrong, and then we reach to a contradiction. That's why they call it indirect proof using contradiction. In this method, we suppose the conclusion or the statement is false, or whatever is stated is false. Then we reach to a contradiction. Okay, this is interesting. This contradiction might be a very simple algebraic fact, mathematical fact, or some assumption that we actually impose to our theorem. Okay, let's see. The first theorem, super easy. 4.5, page 1. Theorem. There is no greatest integer Remember that infinity is not an integer. Infinity is just a symbol. Okay, there is no greatest integer. Okay. How do we prove this? Direct proof, definition, but how do we use that? How do we define the greatest integer? So since it's hard to write down the logic behind a direct proof, we come up with another method. Indirect proof, proof by contradiction. Suppose we can find the greatest integer. Eventually, someday, somebody can find the greatest integer. So proof by contradiction. So this is how we start. Suppose not, and the statement is false. Suppose not, and we have the greatest integer. Okay, what is that integer? Okay, let us call it n. Suppose n belongs to z is our greatest integer. Well, you found it, huh? This is the greatest integer. Well, somebody says, you found your greatest integer. I'm going to add 1 to it. I'm going to add 2 to it. Am I allowed to do that? Of course, it's just simple addition. If I add 1 or 2 or 3 or any other any other positive numbers to n, it gives me a larger number. But if n is our greatest integer, by adding 1 to any number you like, it doesn't matter. By adding 1 to it, we get n plus 1, which is another integer, and greater than n belongs to z, which is larger than n. So where did it come from? This contradiction that if I add 1, 2, 3, or any other number to n and get another integer which is larger than n, it came from this assumption that we have the greatest integer, which leads to a contradiction. So we have a contradiction. This contradiction resulted from suppose not. So this statement cannot be true. So the statement cannot be true. There is no greatest integer. We're done with that. Okay, another interesting theorem. The next theorem says there is no integer that is both even and odd. There is no integer that is even and odd at the same time. Okay. It seems to be a simple fact for me, but this is a theorem. How do I prove basic facts, basic things that you already know? What's the proof behind it? Proof. Since it doesn't make sense to use the direct proof, we're going to use indirect proof, proof by contradiction. So, proof by contradiction. Well, remember that when you're using proof by contradiction, you always start by suppose not. Suppose this statement is not true. What's the meaning of that? It means that its negation is true. So suppose not. Well, okay, suppose not. Suppose not, it means that I can find an integer which is even and odd at the same time. And we can find an integer like n, which is even and odd. Okay, so now our job is to expand this and get into a contradiction. Okay, let's see. Since n is even, n is even, remember the definition of an even number, there is an integer like k such that n is 2k. Since n is odd, we can find another integer like L. There is an integer like L such that n is 2L plus 1. 2L plus 1. Okay, I'm going to use 2 boxes so I don't lose these 2. I'm going to number this by 1, number this by 2. I remember I used a lot of colored pencils when I prove things. Sometimes the proof gets complicated and you need to keep track of the results that you have. Okay, what I'm going to do I'm going to subtract these two. Subtract 1 and 2. Okay, here I have n equals to 2k, n equals to 2l plus 1. The subtraction gives me 0. 0 equals to, okay, I have 2k minus 2l minus 1, or you can just write down 2l minus 2k plus 1. Okay, what do I get here? If I factor out 2, it says 0 is equal to 2 times l minus k plus 1. It says, okay, it says 0 is equal to 2 times an integer plus 1. It says 0 is actually odd. So 0 is equal to 2m plus 1, or 0 is odd. You know that 0 is not odd. The symbol shows that it's a contradiction with the fact that we know 0 is even. So since we reached to a contradiction, what's the meaning of that? It means that suppose not, and we can find an integer n, which is even and odd, is a false statement. So we reached to a contradiction. Where did it come from? It came from suppose not. So the statement, the original statement is true. So the statement is true. So this is contradiction. We say that, hey, our statement is not true. What's the meaning of that? It means that the negation is true. We say that the statement is false, so the negation is true. That's why we start with suppose not. And then we try to reach out to a simple algebraic or mathematical fact that we already know it's true, but we end up with being not true. So that's how we say we reach to a contradiction. What's the meaning of that? It means that the negation of the statement cannot be true. It means that our statement, original statement, is a true statement. This is contradiction. Now, contraposition. Well, contraposition is coming from the definition that we did before when we talked about implication, inverse, converse, contrapositive. The method of contraposition is using the contrapositive of the statement that we have. So, in method of contraposition, instead of proving P then Q, we prove it's contrapositive. So instead of proving P then Q, we prove the contrapositive, which is not Q, then not P, not Q, then not P. Okay, give us an example. This is abstract. Okay, give me a second. So here we have a proposition which says, well, for all integers n, for all integers n, if n squared is even, if n squared is even, then n is also even. Then n is also even. Okay, perfect. What do we have here? We have an implication. We have a hypothesis and we have a conclusion. This is our hypothesis. N squared is even. And then n is also even. This is the conclusion. This is our Q. This is our Q. So it says prove P then Q. We already tried this using direct proof. Remember that. Recall. I haven't started the proof yet. Recall. If we want to use a direct proof using definition, it says, hey, n squared is even 2k, k is an integer. This is our proposition, this is our assumption, but how do we show the conclusion? Then n is equal to square root of 2k. What is our conclusion about n? What is the conclusion? How can I decide about square root? I don't know what to do. Well, luckily for me, I know the method of contraposition. Let me try contraposition instead of direct proof. Let us use contraposition. In this method, I'm going to prove not Q implies not P. So what is not Q? N is not even. We prove the following statement. Not Q, n is not even, n is odd, then n squared is not even, n squared is odd. Well, it's much more easier to prove. Why is that? N is odd. So since n is odd, n can be written as 2k plus 1 for an integer like k. Now I'm going to square this. N squared is equal to 4k squared plus 4k plus 1. Here I can factor out 2, and n squared is equal to 2 times 2k squared plus 2k plus 1. This is another integer, so let's call it m. So n squared is equal to 2m plus 1, which is an odd number, which is odd. Am I done? Yes. So instead of proving directly that if n squared is even, n is also even, I use contrapositive of the statement, which I already know from chapter 2, that these two statements are equivalent to each other. Proving this, equivalent, proving the original statement. So we proved by method of contraposition. So we proved the statement by contraposition. And we're done with our proof. Here.